The James Webb Space Telescope just did the impossible. It broke the Eddington limit and locked its gaze on the oldest known galaxy in the universe, z11. What it saw defies everything we thought we knew about cosmic history. Staring into the abyss of space and finding something that shouldn't exist. A cosmic puzzle so wild it makes astronomers question everything they thought they knew about the universe. That's exactly what the James Webb Space Telescope just did. And folks, this is a story that'll make your jaw drop. We're diving into a discovery that's not just rewriting the rules. It's tearing up the cosmic rulebook and starting from scratch. Picture this: a cluster of galaxies. So ancient they're practically whispering secrets from the dawn of time, caught in the act of doing something impossible. These galaxies, spotted at a red shift of z=12, are shining brighter and working together in ways that defy the laws of physics as we know them. This isn't just a peek into the early universe. It's a time machine showing us a universe that was wilder, weirder, and way more connected than we ever imagined. So, grab a seat because we're about to take a 13.5 billion year journey back to a cosmic mystery that's shaking up everything we thought we knew. Let's set the stage. The universe is 13.8 billion years old. And when we look far enough, we're looking back in time. Light from distant objects takes billions of years to reach us. So, when the James Webb Space Telescope points its golden mirrors at the farthest reaches of space, it's like flipping through a photo album of the universe's baby pictures. Most of what we see from the early universe, say 400 to 600 million years after the Big Bang, is pretty scrappy. Tiny galaxies just starting to clump together, forming stars in chaotic bursts. But this new discovery, it's like finding a fully orchestrated symphony in a nursery. Webb spotted a cluster of galaxies dubbed CLJ12 because of its red shift of 12. That's so old it was shining when the universe was barely 300 million years old. That's less than 2% of the universe's current age. And this cluster isn't just sitting there. It's buzzing with activity that's making astronomers lose sleep. So what's the big deal? Galaxy clusters are like cosmic cities. Collections of galaxies bound by gravity with hundreds or thousands of galaxies hanging out together. Today's clusters, like the Virgo cluster near our Milky Way, took billions of years to form. Gravity pulls galaxies together slowly like a cosmic dance that takes eons to choreograph. But CLJ12, it's like finding a bustling metropolis in the Stone Age. This cluster has at least a dozen galaxies, each one blazing with light, packed with stars. And here's the kicker: seemingly synchronized in a way that's just not supposed to happen this early. Webb's near-infrared camera, or NIRCam, caught this cluster in stunning detail, showing galaxies that are not only bright, but also chemically complex with signs of heavy elements like carbon and oxygen that shouldn't exist in such abundance so soon after the Big Bang. Now, let's zoom in on why this is so mind-bending. In the early universe, everything was made of hydrogen and helium with a pinch of lithium thrown in from the Big Bang. Heavier elements like carbon, oxygen, or nitrogen only show up after stars are born, live, and die in spectacular supernova explosions. These explosions scatter those elements into space where they get recycled into new stars and planets. But that process takes time, hundreds of millions of years at least. So when Webb's spectrograph NIRSpec analyzed the light from CLJ12, astronomers expected to see mostly hydrogen and helium, maybe a hint of carbon from some early stars. Instead, they found a chemical cocktail that's way too rich for a universe this young. The galaxies in CLJ12 are pumping out heavy elements at a rate that suggests either stars are forming and exploding at an insane pace, or something else is going on, something we don't yet understand. But here's where it gets even wilder. Each galaxy in this cluster seems to be home to a supermassive black hole. And these black holes are acting like cosmic conductors orchestrating the chaos. Supermassive black holes, the kind that weigh millions or billions of times the mass of our sun, are usually found at the hearts of big galaxies today. They grow slowly, feeding on gas and dust over billions of years, or by merging with other black holes in cosmic collisions. But in CLJ12, these black holes are already massive, some clocking in at 5 to 10 million solar masses. And they're not just sitting there. They're feeding at a frantic pace, surrounded by glowing accretion disks that shine brighter than the galaxies themselves. These disks are like cosmic spotlights blasting out light. As picturesque as these black holes are, they're not just eating, they're eating in sync. Data from Webb suggests the black holes in CLJ-12's galaxies are all active at the same time, something astronomers call an active galactic nucleus, or AGN. This synchronized activity is like finding a dozen rock bands playing the same song perfectly in tune in a universe that's barely had time to form a garage, let alone a stage. Now, let's talk about why this synchronized behavior is such a head-scratcher. Black holes don't glow on their own. They're invisible, cloaked by their event horizons, the point beyond which nothing, not even light, escapes. But when they feed, gas and dust spiral into them, heating up to millions of degrees and shining like a cosmic beacon. That's what we're seeing in CLJ-12. A dozen beacons, all blazing at once. Normally, black hole activity is sporadic. One galaxy's black hole might be active while its neighbors is quiet, because feeding depends on local gas supplies which vary. But in CLJ-12, it's like every black hole in the cluster got the same memo to start chowing down at the same time. This is a cosmic red flag. It suggests these galaxies aren't just randomly active. They're connected, sharing resources, or triggering each other in ways we don't fully grasp. Point one clue to this mystery lies in how this cluster was spotted. CLJ-12 was magnified by a cosmic trick called gravitational lensing. A massive foreground galaxy cluster called GCL-239 bends the light from CLJ-12, acting like a natural telescope to make it appear brighter and sharper. Without this lensing, Webb might have missed the cluster's details. The lensing let astronomers see that CLJ-12's galaxies are not only bright, but also tightly packed, closer together than modern clusters. This suggests the early universe was denser with galaxies forming in crowded cosmic neighborhoods. Maybe this density allowed gas to flow between galaxies, fueling their black holes simultaneously, like a shared cosmic gas station. But even that doesn't fully explain the scale of what we're seeing. Let's dive into the science for a second, because this is where it gets juicy. The black holes in CLJ-12 are pushing the limits of something called the Eddington limit. Named after astrophysicist Arthur Eddington, this is like a cosmic speed limit for how fast a black hole can eat. As gas falls into a black hole, it heats up and releases radiation. Think of it as a glowing hot disk of doom. That radiation pushes back against the incoming material, like trying to shove too much food into your mouth at once. If the black hole eats too fast, the radiation pressure blows the material away, setting a cap on how much it can consume. For a 10 million solar mass black hole, that's about one solar mass every few decades. But in CLJ-12, some of these black holes are gobbling up the equivalent of 3 to 5 suns per year. That's not just breaking the speed limit. It's like flooring a cosmic supercar. How is this even possible? One idea is that the early universe was a buffet of gas clouds so dense that black holes could feast without worrying about the Eddington limit. Maybe the conditions, higher density, fewer heavy elements, allowed these accretion disks to be puffy or clumpy, letting more materials sneak in without being blasted away by radiation. Another theory is that these black holes form differently, maybe from the direct collapse of massive gas clouds, skipping the slow growth phase entirely. Picture a cosmic shortcut. Instead of starting as a small black hole from a dead star, these monsters might have been born big, collapsing straight from gas clouds thousands or millions of times the sun's mass. But wait, there's a twist. Some astronomers are wondering if we're misreading CLJ-12 entirely. The chemical signatures in these galaxies are throwing everyone for a loop. The high levels of carbon and oxygen suggest intense star formation, with massive stars exploding as supernovae and scattering heavy elements like cosmic confetti. But the ratios are weird. Carbon is way more abundant than expected, almost twice what we see in modern galaxies. This could mean CLJ-12 is in the middle of a star-forming frenzy, with supernovae going off like fireworks, forging elements at a breakneck pace. Another possibility, something called a tidal disruption event, where a star gets too close to a black hole and gets shredded, releasing a burst of energy and elements that could mimic what we're seeing. There's even a wild idea about runaway stellar collisions, stars smashing into each other in dense clusters, creating heavier elements in the chaos. This discovery is sparking a debate that's got the astronomy world buzzing. Is CLJ-12 a cluster powered by synchronized black holes breaking all the rules? Or is it a star-forming powerhouse with black holes playing second fiddle? Maybe it's both. A hybrid where black holes and stars are feeding off the same cosmic fuel, driving each other's growth in a chaotic dance. The truth is, we don't know yet. The data is messy, like trying to solve a puzzle with half the pieces scattered across the universe. Every new observation from Webb adds a piece, but we're still missing the full picture. Why is the James Webb Space Telescope the star of this show? Launched in 2021, Webb's infrared vision lets it peer through cosmic dust and gas, seeing things Hubble could only dream of. It's built to look back to the universe's toddler years when the first stars and galaxies were forming. CLJ-12 was spotted during a program called Cosmos Webb, a deep survey of the early universe. Webb's ability to capture light from 13.5 billion years ago is like having a front-row seat to creation itself. And with gravitational lensing amplifying the signal, we're seeing details that would have been invisible otherwise. Details that are forcing us to rethink how cosmic structures form. Let's talk about those black holes again, because they're just so wild. At 5 to 10 million solar masses, they're not the biggest we've seen. Our Milky Way's black hole, Sagittarius A*, is about 4 million solar masses, but they're way too big for a universe this young. It's like finding a skyscraper in a prehistoric village. And they're not just big, they're active all at once, like a cosmic flash mob. Normally, a black hole eating this fast would choke on its own radiation. But these are somehow keeping the feast going. Maybe the early universe's dense gas clouds let them gorge without limits. Maybe they merged like crazy in a cosmic mosh pit, combining masses in record time. Or maybe our models of black hole growth are just wrong. And CLJ-12 is the wake-up call we needed. This cluster isn't alone out there. Webb's been spotting other weird objects. Little red dots. They call them compact, bright galaxies glowing fiercely in the early universe. If CLJ-12 isn't a one-off freak, we might need to rewrite the story of cosmic evolution. Did black holes form first, pulling galaxies together like cosmic architects? Or did galaxies form, spawning these monster black holes in their hearts? The old idea was that galaxies come first with black holes growing slowly inside. But CLJ-12 and its cousins are hinting at a wilder story. A universe where black holes and stars formed in tandem, driving each other in a chaotic feedback loop. The environment of CLJ-12 gives us more clues. This cluster isn't floating in empty space. It's part of a dense cosmic neighborhood where galaxies were starting to cluster together. These early regions were probably hotbeds of activity with gas clouds collapsing, stars exploding, and black holes merging like it was no big deal. This could explain the synchronized activity. Maybe CLJ-12's galaxies are sharing a cosmic gas tank, fueling their black holes and star formation at the same time. But even that doesn't fully explain the chemical weirdness or the Eddington black holes. Some scientists are proposing exotic ideas. Maybe the Eddington limit was looser in the early universe. Or maybe the accretion disks have a strange geometry that lets more material flow in. These are guesses, but they're the kind that keep astronomers up at night. The debate over CLJ-12 is just getting started. The Cosmos Webb team is already planning follow-up observations, using Webb's instruments to hunt for telltale signs of black hole activity, like specific emission lines or jets shooting out at nearly light speed. They're also looking at the chemical fingerprints to pin down whether stars, black holes, or something else is driving this madness. Every new data point is like a clue in a cosmic detective story, and Webb is our best sleuth. It's not just showing us the universe. It's showing us how little we really know. This discovery is a reminder that the early universe was a wild place full of massive black holes, intense star formation, and clusters that don't play by the rules. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.